Okay, so now let's try to come up with the performance measures that address, in general, the balanced approach to binary classification problems. So I have two classes, positives and negatives. And now let's construct measures that communicate how well I capture positives and how well I capture negatives, and how I kind of trading off one event for another. So this will be the subject of this video. This will essentially lead you to a very important concept of ROC curve and all of the surrounding phenomena. Okay, so let's see. Again, to reiterate, what happened here is I have my prediction success table. So I have here I have true positives. There I have false positives. There I have false negatives. And here I have true negatives. And again, these are plus, positives, negatives, positives, negatives. Now, on the previous slide, we talked about the recall. What is interesting is that the recall is often called sensitivity. I mean, it depends on what area you're in, and different people, different practitioners use different terms, which is why it's important to get exposed to all of these different terminology out there. But the sensitivity essentially gives us a fraction of positives that are predicted as positives divided by the total number of positives out there in the population. So the higher the sensitivity, the greater the percentage of positive events that I'm capturing by running my classifier. In addition to sensitivity, let's also introduce a similar measure which essentially focuses on the negative group. In other words, concretely, let's introduce specificity measure, which is true negatives. So that's how many negatives that my classifier correctly classified as negatives, divided by the total number of negatives out there in the population or in the data set that I'm working with. So as you can see now, instead of focusing on this positive group, we kind of have a balanced approach. We have a positives, a diffraction correctly assigned, communicated by sensitivity, and then we also have negatives and a fraction correctly assigned that is communicated by the specificity. And again, as far as the data set goes, this is my observed y. Let's say plus, plus, minus, plus, 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 minus, minus. And this is my response, h of x. And then I have to select some kind of a threshold in order to make class assignments for my, to construct the y hat. Now, here is an interesting experiment that you can run here. You see, the problem with just looking at sensitivity, specificity, or also recall, precision, is that you have to commit to the threshold. And it's kind of a stretch, because often you don't really know what kind of threshold you want to see. And what's even more important, when you vary the threshold, you're likely to influence all of those values. So let's run a simple experiment here. Let's basically take our data set, and we have these predicted response surface values, H1, H2, X3, H3, etc. And let's sort our data set descendingly according to predicted responses H of x. So what it basically means is that in this cell, I will have the minimum value of the predicted response, and in this cell here, I will have the maximum value of the predicted response. And now let's take our threshold and see what happens to our sensitivity and specificity as we vary threshold from the minimum, from T min, to the maximum, let's call it T max, and all of the intermediate cases. And as I'm doing that experiment, I'm also going to plot my sensitivity over here and my specificity over here. So again, I start with 0. Here's a 1.0. Here's a 1.0. And my sensitivity can be between 0 and 1, and my specificity can be between 0 and 1. So suppose we set the threshold at the T minimum. What happens in this case, well, actually, suppose we set the threshold at the T maximum. So we're kind of saying, okay, any record, it will be classified as +1 if the predicted response surface is greater than its largest value. Well, obviously, in this case, no record will be classified as 1, and so we'll have all records assigned to the negative class. Now, what happens in this case, by looking at these measures of sensitivity and specificity, is that when we have a T max as the current threshold, so the threshold is currently set here, so that's our T, all records are assigned to negatives, and therefore I'm getting the specificity of 1.0 and the sensitivity of 0. So I'm doing a perfect job on my negatives, and I'm completely missing on my positives. Now, on the other hand, if I set my threshold to the minimum value, so let me actually use some of this technology here to erase these things. So what happens in this case is if my threshold is set at the minimum, now I'm going to assign all records to positive outcome. Okay. It's just because my decision rule is like that. So in this case, my threshold is way too low. And in this case, all of the records are assigned to positive group, and therefore I'm having a sensitivity of 1.0, and the specificity dropped down to 0. So again, to highlight this, this is what happens when I assign my threshold to T max. And this is what happens when I assign my threshold to T min. Likewise, if you continue this experiment, and let's say you assign a threshold to some kind of intermediate value of x, h of x. What happens in this case, remember, all my records are now sorted according to the predicted response. So in this case, every observation above this value of threshold is going to be assigned to positives, and every record below will be a negative. And in this case, I will not be capturing all of the positives correctly. I will not be capturing all of the negatives correctly. I will be somewhere in between. So if I plot this point, I can get a point that looks here. Or if I change the threshold up and down, I'll plot a point that looks something like there. And now if I connect all of the points and ignore some of the fine structure out there, then what I'll see is that eventually they should all fall onto a curve that looks like this. And what this curve illustrates, it kind of characterizes the performance of the classifier in general as we sweep over the range of different thresholds. And this curve here is what is generally known as the ROC curve. Stands for receiver operating characteristic, and don't even ask me where that name comes from. I mean, it's a kind of a fascinating topic, and if you're interested, you're welcome to research it on Wikipedia or some other sources out there. So receiver operating characteristic curve. Okay, so now just a few other comments here. What usually happens is that as we vary threshold from T max to T min, we're kind of moving from this side of the curve onto this side of the curve. And it's kind of counterintuitive, and what often you will see out there is an alternative approach where the sensitivity will be coded here, but on the horizontal axis, instead of specificity, people will show 1 minus the specificity. It's the same underlying structure, same collection of numbers. The only thing that changes is that now you have basically this curve here mirrored or flipped around the vertical axis. And in this case, what you will get is the curve that looks like this. Okay? And that's basically what happens, and the curve, this information communicated on this curve, kind of tells you in general what's the overall performance of the classifier that you're looking at. Now, one nice thing about the ROC curve is that you no longer have to commit to any specific threshold, and you're basically working with one specific you vary the threshold over its range, and you're capturing the essence or the performance of your model overall as a binary classifier. Now, one way to look at this curve is now to decide what happens when we have a very good classifier and what happens when we have a very bad classifier. Now, let me erase some of these things here and quickly highlight the following. Okay, so what happens when we have a very good classifier or a perfect classifier is the following. Once we have made our predictions and sorted records here, what we expect to have when the classifier is good, we expect to have all positives to be above all negatives. That's the key here. Because if the classifier is really good, that means that every record that's positive has received a higher score, like think about credit scoring, FICO, etc., etc. And if you now do this manipulation with the threshold, so if you go from T max over here to T min over here, what you will see is that in this case, what's going to happen is that I start at this point. That's the T max. All records assigned to negatives. But as I'm moving my threshold down, I'm getting more and more positive classifications. And at some point, once my threshold is set to this value, that H3 that separates pluses from minuses, my sensitivity goes up to 1.0, but my specificity is still at 1.0, and I have achieved a perfect configuration here. And as I keep lowering my threshold at this point, I'll start losing some of the correct assignments to my minus group. So to make the long story short, in the case of ideal classifier, you're going to have the ROC curve that looks like this. So it fills this quadrant here. So this is my best. This is my best. And this is a kind of the most idealistic case out there. Now, on the other hand, imagine that I have a very poor binary classification algorithm such that whenever I produce, let's say the extreme case, let's say I generated these values of my response surface at random. I mean, that's the worst case scenario. So I haven't learned anything at all. So if I do that, what's going to happen is that now I'll have a mixture. When I sort by those numbers, I'll have a mixture of pluses and minuses. I mean, not maybe necessarily in that a nice pattern, but they'll be kind of intermixed in a random way. And as you do that, and then you now try the experiment of manipulating a threshold from the largest to the lowest, what you'll see is going to happen is that in this case, your ROC curve will trace this 45 degree line, either on this plot or on this plot. And this is the case that we call a random, or the worst. Okay, so this is the worst. And so what we have concluded here is that whenever you report a performance of a binary classifier, you can always represent it by an ROC curve. And that ROC curve will be, in the worst case scenario, at a 45-degree line. In the best case scenario, it will occupy this entire square. And if you now look at simply the integral, or the area under ROC curve, in the worst case scenario, the area under ROC curve will be 1/2, which is shown here. Whereas in the best case scenario, you're going to cover the entire square. And in this case, your area under curve is going to be 1.0. And this part here, AUC, that stands for area under curve, which is a well-accepted feature out there, and that becomes the overall measure of performance as a classifier. And that's why ROC curve is so important, because people use this area under ROC curve all the time. And by the way, as a side note, just because area under curve varies between 0.5 and 1.0, there is an alternative statistic that is simply constructed as 2 times area under curve minus 1. It is known as a Gini statistic. And the Gini measure now is going to change between 0 and 1. So depending on what field you're in, you will sometimes work with Gini, you'll encounter Gini, but you'll see that it's basically, essentially, it's a kind of a scaled version of area under curve. And by the way, this Gini statistic has nothing to do with Cart Gini. That's something that we talk about in some other classes. So by and large, this is what ROC curve stands for, and this is, again, one of a very important performance measure characteristics that you will encounter out there. People often ask, what would be the best value for my ROC? Well, the answer is it depends. Depending on what kind of application you're dealing with, what's accepted in industry, and sometimes, I mean, typically if you're getting ROC, area under ROC into 0.7, 0.8, it's already looking good. Obviously, if you're getting into 0.9 area, that's really good. But you never know. It always depends on any specific situation and whatever is generally accepted. But the good news is that now when you have a whole bunch of different classifiers, now you can rely on the machinery, which is the area under ROC curve, in order to decide which classifier does a better job. Now, of course, we're kind of averaging things out here. So you could have 2 classifiers. They have kind of similar areas in the ROC curve, yet the ROC curves themselves will be quite different. And of course, the ROC curve itself, at every point on the ROC curve, you're kind of assuming that you set a specific threshold. And as you go from point to point, you're varying that threshold. And you can see some dramatic changes in your precision, recall, or sensitivity and specificity. So this is the essence of binary classification, and it's some interesting nuances and difficulties that arise. In the next set of slides, we will look at the next video. We will continue with this topic, but I will have yet another approach to skin the cat, so to say, and that has to do with gains and lift. You'll see that the gains and lift has a direct relationship to ROC curve. It just imposes yet another level of interpretation.